Hello, let's talk recursion and backtracking, commonly used algorithms. So to give some background, recursion is calling a function from the same function with a new set of arguments. It often helps to reduce a problem to this problem of the smaller size and up until the answer is like trivial to compute. Also, you may have to use memorization to prevent evaluating the function with arguments you evaluated before, and you can often prevent the runtime from being exponential in this case, and like often get it under control and be more like linear or like of like space of arguments values. So, and when exponential runtime is unavoidable or when memorization is like not really doable, you can still reduce time complexity by stopping recursion early and trying other combination of parameters if like something doesn't work, instead of doing full brute force. So this would be called backtracking. Let's take a look at some examples. A simple example is Fibonacci sequence. It's computed by a formula fi equals to fi minus 1 plus fi minus 2 for I more than 3, and f1 is 1, f2 is 1. And you need to compute fn for positive integer n. And there are a couple of approaches to this, and one solution is just compute as is, declare function f, and if argument is more or equal than 3, we just do the recursive calls, and otherwise we just return 1 if its I is like 1 or 2. Also note that it's like due to simplicity, you can just do a for loop to evaluate from smaller values to larger values, and it's going to be similar time complexity if you like have memorization for recursion, of course. Because if you don't, then it's like a Fibonacci sequence grows exponentially, so you're gonna have like exponential runtime as well. But with memorization, it should be good. Now a more like complex example is combinations of chess queens. You need to put n chess queens on the n board so that they don't attack each other. On to the right, there are examples of like 4 queens on a board 4x4, and there are 2 combinations. To remind, like chess queens can attack horizontally, vertically, or diagonally. So we would build a recursive function f depth and at positions, like some reference to positions array, which tries to put a queen in a column number depth and maintains a reference to the array of positions of where the queens are on like previous columns. It does a for loop for a row to put a queen, and then like we do another loop checking if it's attacked by any of the previously placed queens. Just compare the values of the rows, and also like deltas between rows and columns and absolute values to check for diagonal attacks. So if it's not attacked, it updates positions and calls fdepth plus 1 and at positions. And notice that when the loop ends, it automatically backtracks because of the nature of recursion. And when depths become n, we increment the answer. So we assume the depth goes from like 0 to n minus 1 for like the positions are from 0 to n minus 1. Yeah, and you can have like variations, maybe with like something like bishops or knights, but then it would be more like complicated because then you can place like more of them in the same row, and it's gonna get like bigger time complexity. But queens is like sweet spot. You can also be asked to print such positions, but then you just do similar thing. You just go through positions, and you need to write a formatting function. Then let's take a third example on. So preorder traversal to inorder traversal. So you have a binary tree of unique integers. And now the twist, where all elements in the left subtree are smaller than the root and all elements in the right subtree are larger than the root for every element in the tree. So you can pick any element as a root of subtree and then like check its subtree of these roots to the left and to the right. So preorder traversal is a sequence where we print the root first, just to print the number of in the root, and recursively print the left subtree and then the right subtree. Inorder traversal is a sequence where we recursively print the left subtree first, then the root, then the right subtree. So, and now given a preorder traversal sequence, find the inorder traversal one. So let's take a look at 4, 2, 1, 3, 6, 5, 7. So 4 would be the root, then smaller elements 2, 1, 3 would be in the left subtree, 6, 5, 7 would be in the right subtree. So we print the left subtree, it's end up unwinding to like 1, 2, 3. We print the root 4, and we print the other like subtrees like 5, 6, 7. So as for the solution, we can have recursive function fij to print subtree from indexes I to j, assuming that's actually a valid subtree and index I is the root. So initial call would be f0n-1, and for fii, it just prints ai, the current value. So on every step, we need to do a binary search on like i+1j to find where the left subtree ends and right subtree starts. That's where the property of this ordering of like elements in subtrees versus root becomes important. Because if it's just arbitrary tree, you cannot do that. And then you find some number k, so i+1 to k is like left subtree, and k+1 to j is the right subtree. Then you like call fi+1k, then print ai, and then call fk+1j. And that's gonna solve the problem. And time complexity is for balanced tree is gonna be linear, because we have like time complexity of like size n is equals to 2 time complexities of size n divided by 2 plus logarithm n, and it's like going to be dominated by the left side to given like linear complexity. But there can be like various such cases when like tree is imbalanced, maybe like a tree is a chain, and in this case you might end up getting n log n in some cases. But it's not the end of the world. So homework. Let's take a look at 3 problems. First one is a person can jump from some position I forward to position i+1, i+2, and i+3. Find how many different ways modulo this like number are there to jump from the position 0 to the position n with some number of jumps. For example, for n equals to 3, the answer is 4. We can do from 0 to 3, we can do 3 small jumps. We can do jump like medium, jump small, jump medium, and we can do like a big jump. Another problem is given a string with distinct lowercase letters, prints all permutations of it in like pseudo-graphical order. For example, for ABC, we have ABC, ACB, BAC, BCA, CAB, CBA. And the last problem, given an arbitrary binary tree, this time without any like specific ordering, but with unique elements, and it's preorder traversal, like root, left subtree, right subtree, and inorder traversal, left subtree, root, right subtree. Find a postorder traversal, left subtree, right subtree, root. So pause the video, try to solve the homework yourself, and then you can come back for analysis of these problems. Okay, so let's take a look. So for the first problem, we can we can do like a simple like recursive algorithm where we just like try to jump in different like three different steps and go forward. But this is gonna have like exponential runtime. You can also like try to like use like check for the last step. Suppose fi is solution for like I. Then you can come from there from like position i-1, i-2, and i-3. And that gives you like different passes. So you just sum up those numbers, take the modulo, and you get a similar formula to Fibonacci sequence just with like 3 numbers. So then you can evaluate it recursively or using the loop. So for permutations, since it's distinct, it's not that hard. You just call a recursive method with like function from like depth. Then we call reference to array with a current set of characters, and also we maintain which letters are already used. So then we like start iterating from like we sort letters lexicographically. In this case, it's already sorted, so we start with like loop with like A's and B's and C to put in the first position, and then recurse to like depth +1 and try to put the remaining letters. And overall, in the end, when we reach depth equals to like length of the string, we add the current sequence to the result. Just add a copy of it. And then for the last problem, we cannot do like this like binary search solution because then there is no guarantee on the like order of elements. But nice thing about it, we know the root. So basically we can find the root in the inorder traversal. So we can have some like mapping. So this mapping can be like from element to where it appears. So then we basically know how many elements are in the left subtree and right subtree by position of the root. So we can like break down this into like, so basically we have two sets of indexes where the subtree is in the preorder traversal and where the subtree is in the inorder traversal. And we have like basically two subtrees in this case. So we like call two recursive calls. We start from 0 and -1, 0 and -1. On every step we just like get the root in where it is in like inorder traversal. Evaluate number of elements in the left subtree and right subtree of that subtree, and call recursive functions with this combination of indexes. And if the lengths become 1, it's just like converges on the same element, and we just print it. And yeah, we first call like this recursive function for left subtree, then to the right subtree, and then print the root. Yeah, that's gonna be it for me today. Please let me know if you have any questions.